Thank you for the nice introduction for me. Yes, and also thank you for attending for my special lecture. So first, I can talk about for my guidance of my lecture. So So this is a brief introduction of myself. I have already given this one. Yes, my name is Yosuke Mizuno, and the nationality is Japanese. And then I graduated Kyoto University, so work as a postdoc research scientist in the NASA Space Flight Center, Alabama, the University of Huntsville, National Simplified University, and then current position is the Institute of Theoretical Physics in the Goethe University Frankfurt. I'm a black hole camp project research scientist. So this is research scientist. Yes, I say this is plasma astrophysics, relativist astrophysics, numerical astrophysics, and high energy astrophysics. So this is the lecture's website. So I put onto the lecture website into my website into there. So in this lecture, I doesn't use for any specific textbook for this lecture. And then after the lecture, I would like to upload for the lecture note into each chapter. So this is keynote presentation file or PDF file onto this website later. So I think you don't need to take it to the note. So after that, you can see about my lecture note. But please hear what I said. Just concentrate to the contents of there. So this is course contents. First, today I talk about for the brief introduction of the relativistic astrophysics, and then to the overview of the Newtonian hydrodynamics, magnetohydrodynamics. So today doesn't start any relativistic, and then tomorrow morning I give a seminar to here. So this is a testing of theory of gravity via black hole shadow. This is my recent work. So this is quite advanced, but if you are interested, please attend for this seminar too. And then to tomorrow, the lecture, I talk about for the numerical method for the solving MHD. But this is still using for the Newtonian MHD to apply for this numerical technique. But this numerical technique is easy to apply for the special relativistic or general relativistic way. So we need first understand the basics there. Then the Wednesday, I talk about for some essence of the special and general relativity, what the difference from the Newtonian way, and what we need to catch up there. Then the Thursday, I think this is the most important part, is the 3+1 formalism of the general relativity MHD equation. We are talking about for the general relativity MHD simulation to solving for the numerically. It's solving for the numerically, we need to separate to the space and the time. So we need some specific coordinate, for some special coordinate with observer to think about there. So we try to say about for this deeply about for how to make it for this setup, then how to solve it for the numerically. Then at the final Friday, I can talk about some application for general relativity MHD case. There. So this is a little bit recommendation of the textbook. This is the Anil. This is the 1990 that show about relativity fluid and magnetic fluid. This is a very basic the textbook, and then this is a very mathematical textbook, but this is very nice. And then I also show about for the two living review in the relativity part. The first part is the relativistic fluid dynamics. This is also talk about for 3+1 formalism part. And then also the 2008 is the font is written for the numerical hydro and the magnetic hydrodynamics in general relativity. This is also all cover for about for the numerical techniques into solving for there. Then I also recommend to my supervisor, it's my black hole camp PI, the Luciano Rezzora's textbook, Relativist Hydrodynamics. This is contained only for the hydrodynamics, but this is very widely covered for the basic of the relative hydrodynamics, and then also the numerical hydrodynamics, and then application of this relative hydrodynamics. So if you think, maybe you can think about it. So this is a notice. So I tried to using for something to mix up for the SI and also CGS unit. So some equation written for the SI unit, some written for CGS unit, because I catch up for some the grabbing for my previous lecture note. Sometimes written to the SI, so I hope it doesn't so much confuse. And then also several equations written into also the SI and the CGS unit completely. But of course, in the astrophysics, CGS unit is more popular, so I think it's better to use. And then also I try to do it for the derivation of the equation as much as I show, but sometimes I miss or even for I mistake. So maybe if you found something, so please let me know today. Okay, and also if you have any question, and also if you say this is too fast.
Whenever you
yeah.
do exchange between the two systems, just remind
yes.
the students about this because sometimes they are not aware.
That yes. Okay. So yes, so if you have any questions, so please anytime you can raise a hand to say something like that. Yeah. Okay. So do you have any question? Nothing. So I can enter to the yeah.
Using the microphone?
Ah yes, using for the microphone. It doesn't. Yeah.
Oh, it's because I'm in the front side.
Ah yes.
So everybody's.
Yeah. Okay. So.
Because we are
yeah.
recording as well.
Yes. So the first lecture is talk about for the relativistic astrophysics and magnetohydrodynamics part. So this is the first talk about for the relativistic regime. So what's the difference to come to here? So now I can write in for the 1, 2, 3, 4, 5 the system if we think about for the relativistic regime or not. So first one is a kinetic energy is much larger than to the rest mass energy case. So it means this is the most of the relativistic system, we say this is the kinetic energy is larger than the rest mass energy. So for example, the fluid velocity is near to light speed. So usually the Lorentz factor is much larger than to one case. So this situation is happened there. So in the astrophysics, the relative jet, ejector, wind, blast wave, and the shock wave, and in the AGN, the gamma ray burst or the pulsar, this is written to this situation there. Second one is the thermal energy. It's larger than to the rest mass energy. So this is typically we can think about for the plasma temperature. It's much larger than to the ion mass energy case. So in this case, we say this is a gamma ray burst. If we believe this is a fireball, this is a magnetar flare also, and then pulsar wind nebula situation. This is situation that happened there. And then third part is magnetic energy. It's much larger than to the rest mass energy. So we say sometimes we are using for the magnetization parameter sigma. This is the pointing to the kinetic energy ratio. So between to the maybe we say the magnetic energy over to the kinetic energy the ratio. If this is the sigma is much larger than to 1, it means the magnetic energy is much larger than to the rest mass energy. In this case, so the alpha wave is going to the near to light speed. We need taking care of the relativistic situation. So in this such kind of situation is sometimes for the pulsar magnetosphere or some very strong magnetic field magnetar case or a black hole magnetosphere also happens there. Okay, so the fourth one is a gravitational energy. It's much larger than to the rest mass energy. So this is a typical criteria for the general relativistic situation. So the GM over C is just the gravitational radius over to R. It's much larger than 1. So this is black hole or neutron star system, or some the white dwarf sometimes also applicable, but mostly the black hole neutron star case situation is happened there. The last one is radiation energy. It's also much larger than the rest mass energy case. Also, we need to think about for the relativistic situation. So typically this kind of situations happen for the supercritical accretion flow. So maybe the Friday I can a little bit talk about for this one also to there. Okay, so this is a 5 criterion to the relativistic regime. So if we need your situation is entered to the one of this criterion, I recommend to using for the relativistic equation. Okay. So this is the application of the relativistic astrophysics. So the big category is coming from the black hole system. So of course, we think about a high and low accretion rate AGN situation or tidal disruption event, X-ray binaries, long soft gamma ray burst, or black hole merger for this gravitational wave source. Everything is related for this black hole. They should be considered for relativistic situation. Second one is a neutron star case. So this is something coming from the pulsar magnetosphere or the direct to the pulsar, and also the quark collapse supernova, and also short hard gamma ray burst or neutron star neutron merger for the gravitational wave source. This is also need to consider for the relativistic situation. Then this is both black hole and the neutron star. This is central system. So this is the source of to the center part. And then so the if sometimes show about for jet and relativistic wind. So this case it's also seen about for the extragalactic jet or the outflow, or pulsar wind jet, pulsar jet, or the microquasar and the gamma ray bursts. They also see about for such kind of the relativistic outflow situation. So we need to also think about for the relativistic case. And then fourth one is also, this is quite new part, but this is laboratory physics into the Earth. Also need to think about for the relativistic situation. Typically, this is a relativistic heavy ion collision situation. It also need to think about for the relativistic hydrodynamics. And then so the plasma laboratory experiment also sometimes think about for the relativistic regime, but this is also some special case. So now we are sure about for this is for the big categories. I think the relativist astrophysics is also nicely overlap or widely using for to the situation to the astrophysics system. Okay, so this is the relativistic. I think it's a many one it's know about for this one. So the relativist jet is the outflow of the highly collimated plasma. So that this is seen about for the microquasar, active galactic nuclei, and also gamma ray burst. So jet speed is near to the light speed. So here I can show about for the one of the most the beautiful system of the radio observation of the M87 jet. So that this is the most largest the size of the M87. I think this is a 100 kiloparsec size. And then if you focus on, you can see about for this is jet structure over there. If you see about for the focus on there, so that we can see about for the jet structure is a multi-frequency. This is the X-ray, this is optical, and this is the radio. And then if you see about for the more that's close to the center part, still we can see to the nicely jet future onto the this system. So now we can see about for the some length scale over there. So the Shiba-Shit radius is around to the 10 to 15 to 10 to 16 centimeter. And then to this very high emission region is maybe coming from the near to the black hole shadow size, the horizon scale. So I think around to the 10 to 17. And then so now it's a VLBI resolution using for the 43 gigahertz here. So this is a resolution is around to the 100 to 1000 the gravitational radius size. Of course, I can talking about for my collaboration work with the event horizon telescope. This is touching for the actually touching for this event horizon size there. So I can also talk about for the tomorrow at the seminar and also the Friday also a little bit covering for this. And then this is the kiloparsec the plasma size. It's around 10 to 22. This is length size, and this is full size of the M87 is around 10 to 23. So we can doing for the simulation between to the 10 to 15 size over there. Then if you think about for the whole structure, we need getting for the such huge length scale we need covered there. So okay, so this is the key issue for the relativist jet. So what's the acceleration mechanism? How to making for this collimated structure over the jet, and then how to propagate it successfully, and then what's the stability of this relativist jet. This is one of my research topics, especially for the stability and how to making for the propagation jet. And the modeling for the jet production also mostly we can use for the magnetohydrodynamics, because this is the large scale plasma we can applicable. Then we also think about the relativity. If you think about for near the horizon region, we think about the general relativity. And then if you think about for the little bit further up to the horizon region, we can special relativity think about. And then also we can observing for the emission. So we need some modeling for the emission also. So this is need about for the particle acceleration mechanism and also radiation mechanism. Also both need about to understand the relative jet. Okay, so relative jet in the universe. So that this is very common to see. So this is the AGN quasar. It's show about for the center it's maybe black hole, and then surrounding for the accretion disk, and then making for the some relative jet, making for the this is radio low. Lorentz factor is around to the 10. This is the typical number, and then this is size of this is kiloparsec to the megaparsec sometimes size. So this is the microquasar. So microquasar center is maybe stellar mass a black hole surrounding for the accretion disk, and then also we can see about the relative jet. It's a typical Lorentz factor is around to the 3. And then we also see about the radio lobe to there. but this is the right year scale because this is micro quasar, stellar size case, but completely different scale, but picture is very similar to that. So gamma ray burst, I think mostly the long duration gamma ray burst case, we can say making for the black hole to the center and then gravitational collapse, and then maybe forming from to the accretion disk, and then making for the relative jet. So the typical Lorentz factor is around 100 in this case. To there. So this is the plasma dynamics vicinity of the black hole and the shadow. So I think that my simulation or my recent work is mostly doing for how the plasma dynamics is happen near to the black hole region. So I show about for one of the recent general relativistic MHD simulation by our black hole accretion code. We say back code. So this is the density we can see about for the equator plane, and then this is also density show about for the vertical plane. So initially we can assume for the accretion torus with the weak single magnetic field loop. So inside the torus we count the turbulence by the MRI, and then the Poynting flux dominated jet is developed there. So after that we can post-processing to calculate the radiation image by using for the general relative radiation transfer code. Then we can see about for this kind of the shadow structure. Maybe it's a little bit hard. Maybe it's yeah. So this is center of the black hole, and then this is the bright emission region to here. So now we can obtain for the black hole shadow image spectral light curve, maybe additional the polarization with this 3D GRMHD simulation to cut into here. So I try to say about for this one onto the Friday onto the tomorrow seminar, the more detail of it. Okay, so this is the one of them. So why we can doing for this kind of things? This is maybe the international collaboration project or the very long baseline interferometry at the millimeter or sub-millimeter wavelengths with the Event Horizon Telescope project to maybe catch up for this shadow the event horizon scale up to the black hole shadow image. So this is the Event Horizon Telescope. We are show about for the creating for the virtual radio telescope the size of the Earth to using for the shortest wavelengths to here. So now we are observing for the 230 gigahertz. This wavelength is 1.3 millimeter, 3 millimeter wavelengths, and the diameter is around to the 10,000 kilometer. This is almost Earth size. Then if you think about for the resolution is usually lambda over to the d is around 25 micro arc second. So this is almost touching about for the event horizon size of the Sagittarius A star. This is our center of the galaxy and M87 case. So this is nearby a large radio galaxy. So
is this the perspective of Sagittarius A star?
Hmm?
Is the Earth is being seen from the perspective of the galactic center?
I think this is yes. Yeah, no, I think it's not this one. Yeah, I think we can try to say about for the Earth what kind of the telescope we can connect it here. It doesn't matter to where direction over there to see this. Yeah, so this is also the where we can what kind of telescope to there. But I think it's some telescope it doesn't including to here. This is also still including SMT here. Yes. So this is some spectra to calculate over there also. Okay. Yeah. Go. Okay. So this is the actual the Event Horizon telescope into observing for the 2017 in April. We are first time to including for the ALMA, including for this Event Horizon telescope of the observation. So this is including for the 1, 2, 3, 4, 5, 6, 7, 8 telescope antenna including here. One of the biggest one is ALMA, and then this is ALMA and Apex, JCMT in the Hawaii, and the LMT in the Mexico, and the Iran, and this is the Spain, and the South Pole telescope, and then in the South Pole, and then to the 7 millimeter array SMA in the Hawaii, and then SMT into the Arizona. So this is the 2017 observation we can including for this the telescope, and then the 2018 we can add to the this telescope, including for the this is JCMT, SMA, SMT, LMT, IRAM, and ALMA, SFT, and then new telescope coming for the GLT in the Greenland telescope today. Unfortunately, we lost the, it's picobelta should be included here. No, it's there. Yeah, picobelta is dropped, but still including for to the Iran inside there. So this is the 2018 observation. Then we are also planning for to the next April 2019. Yeah, to continuously observing. So this time it's GLT is involving, and then maybe some other new telescope involving. I'm not sure yet currently. Yeah. Okay, so this is the event horizon telescope situation. So maybe we are still handling for this 2017 observation data to making for the nice result. Then hopefully we can get into the image or some nice result into the early next year to hope today. Okay, so to come back to the next slide, this is starting for the fluid dynamics. So fluid dynamics deal with the behavior of the matter into the large, the average quantity per unit volume, onto the macroscopic scale large. So this is large compared with the distance between the molecule today. Yep.
Just a question.
Yes.
The fluid dynamics that you present now, it will be applied to the jet emission or to the jet propulsion, to the jet production?
Okay, the jet production is we can applicable for to this fluid dynamics, but the emission is we need additionally assuming to there. Yes, so we can make it for the structure of the some jet future like this. Maybe it's easier to say about here. So this is a fully general relativistic magnetohydrodynamic simulation we can do. So we can handle it for the fluid information like this density, velocity, magnetic field is locally. But based on this information, we need also calculate for the radiation. Here we can assume for some the synchrotron emission, but this is non-summer the synchrotron emission, but still we need to think about what's the electron distribution to there. Here we are assuming for the temperature is profile some temperature is proportional to the electron temperature. Then this is making for some summer distribution to making for this emission. So still we need some assumption to based on this plasma behavior to making for the emission between the there. Okay, so this is fluid dynamics. So the fluid is we can think about for the macro dynamics, the macroscopic behavior. It's assuming for the continue to the structure and to the physics quantities. This is such as the mass, density, momenta is contained within to the given small volume to regard the unit spread over the volume. So quantity is characterized as fluid. This is the continuum limit as a function of the time and the position, both of them. So now we are writing for this is density. Density is this is scalar field. So we say only for the time. Then the velocity is become to the vector field, and then the pressure tensor is also tensor field. Tensor field making for the 9 elements. Vector is making for the 3 components, and then density only for the 1 component over there. Okay, so this is the fluid approach to the plasma. So the fluid approach is described the bulk property of the plasma. Of course, the plasma is we are thinking about for the microscopic process to the macroscopic process. The microscopic process simply we can think about for the ion it's moving from to the electron something, and then this is collective behavior like this Boltzmann equation something. Then we are thinking about for the fluid. Fluid is the most large scale macroscopic behavior. To catch up to there. Then this is the bulk property. So we do not attempt to solving for the unique trajectory of the all particle in the plasma. So this simplification works very well in the majority of the plasma, especially from the astrophysics case. So fluid theory is followed directly from the momentum of the Boltzmann equation. So I doesn't say anything detailed about for the Boltzmann equation, but this is each of the moment of the Boltzmann-Brasov equation in the transport equation describes the dynamics of quantity associated with the given power up to the velocity. So this is the continuity mass and the charge transportation, and then this is a momentum transportation, and then this is energy transportation equation. So something this is coming from the Boltzmann-Bratov equation. So, but this is starting point to getting for the plasma to making for the macroscopic case.
N is number density, right?
This is the numbers, but we can think about for the this is only for the number, so particle number. We think about mass or charge. This is depend on the case. Later I can talk a little bit more.
And this is the classical approach.
Yes.
No relativistic.
Yes. So here everything is starting for the Newtonian way. So this is classical approach, going to the Newtonian hydrodynamics MHD. Then I can extend it to go into the relativistic way. Okay, so this is, of course, we can start import the Boltzmann equation into the relativistic way to also writing for the general relativistic hydrodynamic equation directly. But I think this is the same way we can follow this way. Of course, a little bit different to what the seeds comes from something like this, but yeah. Okay, so this is a single fluid theory. So under the certain circumstance, the appropriate to consider entire plasma as a single fluid. So do not have any difference between the ion and electron. Typically, this is the plasma including for the two charge. Of course, ion, electron, positron, electron case. But usually, most of the cases, ion, electron. And then the single fluid theory is both everything mixed together. So we can only one fluid inside of the plasma. So this is approach is called the magnetohydrodynamics. Then so the general method for this modeling, this is highly conductive fluid, including for the low density astrophysical plasma. See we can applicable this one. Then this is single fluid approach. It's appropriate when dealing with the slow varying condition. So this is system is very because of keeping for the plasma structure to within time to time. So MHD is useful when the plasma is highly ionized and the electron and the ion are forced to act in the unison, and either because of frequency collision or by the action of a strong external magnetic field, it's there. So this is the single fluid theory. So we can try to start what's applicable for the hydrodynamic application first. So to apply for the hydrodynamics application, so we need such kind of condition. The spatial scale is much larger than to the beam free path, or time scale is much larger than to the collision time scale. So this kind of situation we can apply for the hydrodynamics. So they are necessary to satisfy the many astrophysical plasma. So typically, if you think about for the solar corona, galactic halo, or cluster of galaxies, sometimes situation is dropping because the mean free path is so much large, something, but still we can applicable. So somehow, this magnetized plasma, its effective mean free path is given to the ion Lama radius. So in this case, even for the mean free path is larger, but ion Lama radius becomes smaller, still we can applicable for this MHD situation. So if this, the size of the phenomenon is much larger than to the ion Lama radius, so the hydrodynamic application can be used. This is our general understanding currently. Of course, there's many one it's claimed this doesn't applicable hydrodynamics, but maybe you can try to do it for the big type of simulation. Then compare to the MHD, what kind of a situation to see? Maybe we can get in for the very similar result to both. Yeah.
Formally,
Yeah.
when, within the plasma context, then the mean free path is provided by the Larmor radius.
Okay.
It should be MHD
Mm-hmm.
application in the sense that we need to complete the hydrodynamic.
Okay. Mm-hmm.
Description, but I'm sure that you are going to discuss this issue.
Yeah, because this is the first think about for the hydro. So hydro is only for the mean free path is given to the information, to the hydro approximation. But yes, as Betty said, if we think about for the MHD, so this is MHD additional information coming for this Lama radius. Then this is applicable for this Lama radius to think about for the hydro approximation. Yeah. Okay, so this is the applicability of the MHD approximation. So the magnetohydrodynamics describes the macroscopic behavior of the plasma if this is spatial scale is larger than to the ion Lama radius and time scale is larger than to the ion Lama period. Okay. So this is the most. So in this case, it's most of the situation think about for the MHD, but MHD cannot lead to the particle acceleration or origin of the resistivity, or pure electromagnetic waves, or some other things. Also, the kinetic effect doesn't applicable for the MHD because magnetohydrodynamics is completely the macroscopic behavior of the plasma. So we can think about for some fluid properties nicely to coupling with the magnetic field. But if think about for the kinetic property to regulate the particle acceleration, we cannot apply for the MHD. Okay. So this is the fluid motion. So the motion of the fluid is described by the velocity field, and which is mean velocity of the all individual particles, which makes up the fluid at the position r, and also particle density nr. So we discuss the motion of the fluid at a single type of the particle, mass and charge. So this is mass is written m, charge is q. So the charge and mass density is qn or mn. So this is n is a number density. So qn is the charge density, and the mn is the mass density to come up. So particle conservation, the equation, this is coming for the continuity equation. You can write in for this one. So the previous, remember. So this is the partial time derivative of n to the nabla dot nv. So this is expand to the this nabla dot to get in for the this equation. So the partial derivative n plus v dot nabla n to the n nabla dot v equal to 0. So this is the first two terms is coming for the convective derivative. You can see about for here. Sometimes we can see about this is capital D over to the dt is written to here. So the continuity equation it can be written to here, this kind of way. Okay, I think it's very familiar to the hydrodynamics. So in the hydrodynamics, we have two different viewing points. One is the Lagrangian viewing, second one is the Eulerian viewing point. So Lagrangian is a sit onto the fluid element and moving with it as a fluid move. So this is the Lagrangian point of view. This is velocity here. This is our system. So we can follow to this system to how to change info with one. Eulerian viewing point is sitting at a fixed point in the space and watch the fluid moving through to this your volume element. So this is identify the fluid in the volume and the content to the change to here. So you can see about the sitting same point, and then how much is the fluid would enter to changing to moving out something. So this equation to here, so the partial derivative part, it's to the time derivative part, is given to the ratio rate of the change at a fixed point. And this is coming for the Eulerian point of view. And then so that this is the capital D, the t term. This is the partial derivative t plus the v dot nabla. This is given for to the rate of the change at the moving point. This is mostly writing for the Lagrangian type of viewing. And then an additional point is the v dot nabla. It's also getting from the change due to the motion. So that we think about for solving for this equation to the previous one. This is into here. So we have the two meaning. So this is how to change in for the moving point, and then how to change in for the one point over there. So this is single fluid equation for the fully ionized plasma. So that we can combine to the multiple fluid equation because of the Brasov or Boltzmann equation. We don't worry. We are usually separate to the electron and ion. But this is MHD. Also, the single fluid MHD we can think about. We need to combine together to the electron and ion, both of them. So that into the set of the equation for the this is single fluid. So first we can assume for the two species plasma for the electron and ion. Now we are writing for the J. This is E or I. So this is the continuity equation first, and then this is momentum equation to both of them. This is shown up for the previous the Boltzmann equation to see that there, so to here. It's a continuity mass transport and the momentum transport equation. Okay, so for the fully ionized two species plasma, so the total momentum must be conserved. So it means the P, this term is EI equal to minus IE. This is exchange for the momentum for electron to ion, ion to electron. This is same. And also that if think about the electron and ion, so the mass difference is very large. So in this case, it's the ion mass is much larger than to the electron. And then so the time scale in the continuity and the momentum equation for the ion and electron are very different. So the characteristic frequency of the plasma frequency, cyclone frequency, also much larger than to the electron. So everything is dominated for the ion situation, if you think about for the larger scale. So when the plasma phenomena are the larger scale, so this is typically the system is much larger than to the Debye length something, or even ion Raman radius, and then the relatively low frequency and the average plasma, the electrical neutrality also think about. Then the independent motion of the electron ion can be neglected. This situation we can think about for the single fluid plasma. So we can treat the plasma as a single conducting plasma. Then the inertia provides the mass of the ion only. Then this is governing equation are obtained by the combine with the two equations. So this is electron and plus ion. The first, I try to describe to the equation. First, we can define to the macroscopic parameter of the plasma fluid. So here I can just write in for the density the rho m, but this is mass density. Tomorrow I can just only for the rho. But here the mass density and then to the so this is the electron the number density times to the mass of the electron plus the ion number density times the mass of the ion. This is the charge density. Charge density is rho e, we can write. So this is Ne times to the charge of the electron, and then number of the ion times to the charge of the ion. This is go together. So this is electric current. Current is NQ times to the velocity. Then this is both electron and ion we can catch up here. Then typically this is Ni and NQ is the same, so we can think about for the B minus A, this is electric current. So velocity is something we can get in for this is Ne and me to the velocity, each velocity of the electron and ion, and then divide to the density. This is we think about for center mass of the velocity. So this is system is over there. We can collect in for the all density, and what's the center of the mass, we can move in for this situation. So pressure is also just getting for the both contribution to electron ion. So we are using for the rho m, rho e, j, velocity, and the pressure. We try to write in for this equation. So first, using for the continuity equation, this is still writing for the j. So this is given to the electron or ion. So the multiply to the QE or QI and add to the continuity equation. Then we can get in for this charge conservation equation. Easy to do. So where is the J is the electric content density. So this is written to here. And then rho E is this is electric charge. So previously we can define to there. This is charge density and electric current. So we can get into directly this equation. Similarity, we can use it for the multiply to the mass of the ion and the mass of the electron. We can get in for the mass conservation and the continuity equation over there. So here, of course, rho E, rho M is this is Ne times Me to the Ne. So both the electron and the ion combined together is a single fluid mass density, and the velocity is a fluid mass velocity over to the rho M. So it means this is center mass of velocity to there. Okay, I think you can this is familiar to this mass continuity equation. Then we are going to the next is equation motion. So equation motion for this is bulk plasma can be obtained by adding to the individual momentum transport equation for ion and electron. So previously I can use it for the continuity equation of the number density case. So here we are getting for the equation motion to using for the momentum equation. So right hand side of the momentum transport equation, maybe you can recap again to the equation to here. I try to use it for here. This is left hand side. This is right hand side equation. So left hand side equation it's right in here. So this is difficult. This is a convective term. It's non-linear here. But we note that since the electron mass is much smaller than to the ion mass, this is contribution to electron momentum is much less than to the from the ion. So we ignore it into the equation. So just only think about for the ion in this situation. Then we also approximate the center of mass velocity, its ion velocity. So this is velocity, it's almost similar to the ion velocity because the big mass is big moving, it's just only contributed for the ion case. Then this left-hand side momentum equation, it's written to the approximately written this kind of way over there. So this is getting for to the normal density, and then this is the velocity over there. So this is the left-hand side. So next, consider for the right-hand side of this momentum equation. So this is a right-hand side momentum transport equation to there. In general, this is second term. This is electric body force. It's much smaller than to the J cross B term. So we can ignore it. So we can just right-hand side coupling with the left-hand side, right-hand side. This is equation motion to the equation. But here we can use it for the P called capital P, we say, because this is still the pressure momentum, it's a tensor situation here. For the isotropic plasma situation, this situation is just only for the diagonal term, the P. So we can just simply the scalar vector, its scalar point is the P. And then where the total pressure, its pressure P is the electron and ion contribution, both of them. Then we can write down for the this equation motion. It's maybe you can familiar into the fluid equation to there.
So
Yep.
In the first equation, the electric body force is much smaller because of the bi-shielding.
Because of the phase neutrality of the plasma.
Mm-hmm.
Yeah, the bi-shielding.
At the larger scale, because the device in kinetic scales, but
Yeah. Okay, it's already just answer what it should be fine today. Yes.
oh, sorry.
Yeah, it's okay. Yes. If you know, you can answer to that.
So do you agree?
Yeah, of course, it's agree. Yes. Yeah, that's right. Yes. Yep. Yep. So the next is think about for the generalized Ohms law to there. So this is first, the final is a single fluid MHD equation describes the variation of the current density in the J. So this is considered the momentum equation for the electron and ion again to here. Then this is multiplied the electron equation by the QE over ME and the ion equation by QIMI, and then both adding, we can get in for this kind of long equation over there. So this is the starting point of the Ohms law. The generalized Ohms law. So now we ignore the second term on the left-hand side, as we did with a small perturbation. We just take over there. So we try to see about what this each component. So first, for the electrical neutrality, the plasma. So we say this Qn is similar to the Qi and using the J and the B, and we can rewrite in for this equation like this. So now we are see about what this is the time derivative of the current. Then this is contributed for this PE, PI, and then if E plus P cross P term, J cross P term, and then to the PI. So here, still we see about for the contribution both the electron and the ion is coupling together. So here we consider about for the electron mass is much smaller than to the ion mass, and then in this case, QE over ME is also much larger than to the QI of MI. Similarly, we think about the NE QE square term, this part, is also much larger than to the ion term. In the thermal equilibrium, also the kinetic pressure and the electron is smaller than to the ion pressure. So this is here. Then we can rewrite in for the equation to like this. So still we have a 1, 2, 3, 4 term is left over to the generalized Ohms law. So next we can see something about that. So collisional term can be to here. So we are this is empirically we can write in for this kind of the equation. So this is where the eta is a specific resistivity. Then Q square is related to the fact the collision and result from the Coulomb force between the ion and the electron, and the total momentum transfer to electron and the elastic collision with ion is coming from this equation part of it. Yeah.
I think that I missed the point.
Yeah.
We have two components.
Yes.
The electrons and the ion.
Yep.
The ions are much heavier than the
Electron, yes.
than the electrons, but the velocity
Yeah.
of the volume elements,
Mhm.
it seems to me that you have identified with the velocity of the ions
Yes.
because they are much heavy.
That's a yes. Center of mass, yes. Yep.
No, I'm thinking about the kinetic energy because the kinetic energy of each
Yeah.
component depends of the mass but of the squared velocity.
Mhm.
And then the mass is smaller for electrons, but the velocity must be
Yes.
greater. And
Yep.
then what component should define the velocity of the volume element?
This is coming from the yes, is ion. So because we are thinking about for the bulk motion of the fluid. Of course, we have the electron is moving for the more faster to go into there, but we are thinking about for the what's the fluid. It's mix about the electron and ion. It's big to one volume. So this is one volume is just moving. We say this is bulk velocity. This is everything coming for the ion.
Is the center of mass of the flow is determined mainly by the ion component, right? If you agree with the velocity that is provided by the center of mass of each element of volume that has electrons and protons, right? In that expression, that term is dominated by the VI component in the velocity. But you are right in the sense,
Yep.
of course, we do not have the time to discuss
Yes.
the whole effect.
Yep. I think we can catch up for some the general Ohm's law. It's including for the whole effect inside here. But I talk a little bit more later. But this is generally we can drop off this whole effect. But some application for the physical situation, whole effect is something very important. Then this is also getting for some the crucial structure changing of the system. Yeah. So this is now it's written into this is equation to here. This is the whole component. We say this is a generalized Ohm's law. But this is full description of the Ohm's law. But we are thinking about for some more situation to here. So the first the steady current in the uniform the electron. So this is the time component of density is 0, and then to the nabla dot p equal to 0 and the velocity equals 0. So the electron equal to the eta j. So this is j equal to 1 over eta e. So this is the steady current situation today. So in general form, the electron field E, it can be found to this kind of equation over there. So here we can write in for this is rewriting for this basic equation over there. Then this is first term is this is the electron associated with the plasma motion. And second term we say this is the Hall effect. Third term is coming for the ampolar diffusion from the electron field generated by the pressure gradient. And then fourth term is ohmic loss over the Joule heating by the resistivity term. And then fifth term is we say this electron inertia. So this is each what the electron is contributing for this different effect. This is generalized Ohm's law, including for all effect of it. But now we are assuming for the plasma is isotropic, so that this is the number of p term. It's just only for the scalar pressure, and also that we neglect Hall effect, ambipolar diffusion in generalized Ohm's law, since not important one fluid MHD. But this is usual case. But some special case, this form effect or ambipolar diffusion become very important. So typically, I think it's a star formation case. It's now it's minimum is considerable for this kind of effect to now. And also the slow variation is J equal constant, so we can write in for generalized Ohm's law as
Yusuke,
Yes.
I have a comment on this.
Yes.
The ambipolar diffusion
Hmm?
term, because actually it is present
Yep.
only if you take into account the fact that there was the neutral component,
Okay.
right? In the sense that far in this description, this very simple description
Mhm.
that you adopted of a single fluid,
Yeah.
you have accounted only for the ions
Yes,
and
yes,
the electrons,
that yes.
right? But you are right in the sense that eventually, if we consider an extra
Mhm.
term that comes from the collision
Yeah.
between the ions and the neutral part
Mhm.
of the flow, then this can introduce
Yep.
like a pressure term
Yes.
over there, and then it will be similar. It will
Yep.
deal with this. This term may deal. This
Mhm.
extra term will deal with the
That yes. So here, yeah, we are assuming for the
yeah.
this is fully ionized case. Of course, it's sometimes nature including for the
Yeah.
neutral component. Yes.
Yes, and then you have this collision
Yeah.
extra term.
Mhm.
But yeah, of course, you are reviewing very
Yes.
quickly.
Yes. I think yeah, this is yes. So now we are concerned about for the one fluid equation. Then we think about for the more the higher freedom. Think about for the multi-fluid the fluid explanation. Then we can go in back to the Boltzmann equation, or this is more it's particle single motion everything. This is some hierarchy to the
Yeah.
application and to the simplification. Okay, so the yes, so this is rearranging for this equation to there. Then we can write in for the J equal to the sigma. This is E plus B equals B. So sigma is 1 over eta. We say this is electrical conductivity. So this is one fluid MHD Ohms law. This is mostly we can use it for the very simplest situation for the Ohms law. For there. Okay.
Do you guys,
Yeah.
let me ask to the students properly. Do you guys have, I understand that I know most of your faces, so I know that most of you do have familiarity with the classical MHD equations. Just let me know if this is straightforward for everybody, if you are following this description, right? And you can ask questions, right? Because
Yep.
questions always help a lot, not only you guys, but your colleagues on your side, okay? So
Yeah.
if you have questions,
Yes,
ask me
of course.
right, during the course. Do not wait for the end of the class,
Yeah.
right?
So at this year now I think about for the 40 slide, and then now it's very quickly come to about just only for the 1 hour now. So that I still left about 1 hour, but it's yeah, maybe I can this time I can finish a little bit earlier. But of course, if you are too early, too fast, so please stop me and then to ask the question, what the meaning, what the, again, please explain again something like this. Yeah, please give to your understandable things. Yes.
These questions that Ademir and Rodrigo made are very key questions, because sometimes you simply forget, if you are not used to the equations, you forget the meaning of that approximation, of a given approximation. So please ask me questions, because this is still Newtonian, non-relativistic, but when we move to the relativist part, it's going to be even more complex.
Yep.
So,
Okay, one question. For instance, even in Newtonian regime, you can have gravity, so the results holds if you include Newtonian gravity in the equation.
Yes, this is a good point. Yes, currently I doesn't write in for any gravitational term, but of course in general we can put onto the gravitational term. Yes.
both as an external term or as self-gravity.
That's right. Yes, external terms. Yes. So self-gravity. Maybe this is related for the tomorrow. I talk about how to solve for the hydrodynamic equation, but I haven't touched for how to solve for the gravity term equation. So usually this is need to the Poisson equation. So this is some special treatment to take care, but this sorry I couldn't include in that.
Yeah.
I have a small question. Electric conduction means that you have a heat production in the medium.
Yeah.
And then considerations from entropy production is important. Do you think that this Ohm's law can be derived from thermodynamic considerations?
We can handle for some yes. This is the most simplest situation. We can just only for the eta term. So it means that this is Joule heating well, yeah, Coulomb collision, just only consider about there. But this is, yeah, maybe we can mistake up to some additional heating term or something. Of course, if think about for the, now, yes.
Actually, it
Yes.
does. In some sense, it does, because
Yeah.
thermodynamics is also derived from Boltzmann equation, and this also is, when you integrate the moments of the equation, you end up with these terms, including the resistive term.
Yeah, the same thing.
as
Yes.
well. So at the end.
Yes.
Because other we may think this like a constitutive relation to the fluid.
Mhm.
And for instance, the relation and the stress, the viscous stress,
Mhm.
and
Yeah, this is, yes, important point. Yeah.
The
the
source
quantities,
term.
Yep.
the dynamic quantities may be derived
Yep.
from a thermodynamic viewpoint.
Yep.
But I haven't seen a derivation of the Ohm's law.
No, I think, yeah, because here also that we can think about for the, yes, this is pressure anisotropy situation, but this is mostly we can simply assume about for the orthogonal situation. But in general, we have a full component for the pressure is a tensor term. So this is also coming for to the current there.
And if the current depends on time,
Mhm.
Ohm's law should be modified or not?
I beg your pardon.
If the current depends
Current,
on
yes.
time,
I think it's almost
we are
doesn't.
not in a stationary regime.
But
And then I ask if this generalized this Ohm law should
Mhm.
be modified or not.
actually, this is not steady state. You see, you have that equation over there, del J, del T. It's not steady state. You have the Ohm's law is derived out of the equation of motion. When you combine the two, the electron and proton equations, you end up with that relation for the.
I am
Oh,
asking
yes.
because the inertia,
Yeah.
of the ions
Mhm.
or electrons is not taken in account by this expression. For instance, if you take A equal B equals 0,
Mhm.
J is 0, but
Yeah.
in general conditions,
As a matter of fact, it is, Ademir, because it's incorporated in the whole term, actually. Yeah, it implies, that equation implies this approximation of phase neutrality,
Mhm.
right? The two approximations. The
Yep.
conservation, the center of mass velocity, right? That is dominated by the ion part, plus the phase neutrality condition, right? Or in other words,
Mhm.
that approach, the approximation that the charge of electrons, the charge density of electrons is equal to the charge density of protons, right? So perhaps if this condition
Mhm.
is kept over there, if we drop the condition of phase neutrality,
Yeah, this
this
is.
extra term
Yeah, it's
that
come out
he
to the,
wants
yes.
will be there.
Yeah, usually if this is more deeply to the this kind of the heating flux is how to coming from the this is source term to equation to energy conservation equation, then this is I think, yeah, maybe, yeah, Ohm's law is a little bit changing, but I don't remember to that.
Yeah, it will, because this
Yeah.
term will.
Of course, initially we can assuming for the MHD, it's single fluid. This is charge neutrality, everything is assumed. So this is the most fast assumption to doing for the MHD. So it doesn't consider about this kind of
But
situation.
it's going to appear as a term in terms of the velocity, because the velocity here is already the bulk velocity, the velocity of the center of mass. If you take into account that there is this separation, this term should appear there as a correction. V would be VI plus this correction that in turn depends on J, right? Yeah, so there are several terms that you can incorporate if you change the hypothesis, if you include neutrals, for instance, things like that.
Okay. So, yep, this is the simplified MHD equation. So that this is the set of the simplified MHD equation. It can be written into the mass conservation here, and the equation of motion, and then plus to the this Ohm's law equation. So this is a fluid equation. It must be solved with a reduced Maxwell equation. So including for the Maxwell equation into here. So this is displaced current term is ignored for the low frequency phenomena because this is a Newtonian case. But of course, in the GR, we need important part. Here, we also have assumed that there is no accumulation of the charge. So this is rho e equal to 0. This is also another assumption. Then this is a complete set of the equation only when the equation states for the relationship between the pressure and the density is specified. So here we can just written for the very simple polytropic type of the equation state to here. So this is red the circle. This is complete set of the MHD equation. Here, okay. So next is we try to make it for the more simplified for this equation. So first is think about for the induction equation. So here is the taking from the curl of the this is one fluid MHD Ohm's law. This is coming to here. So this is the curl E equal to the minus the curl V cross B plus 1 over J sigma is the curl J. So this is assuming for the sigma equal constant, and then to the substitute for to the J equals the nabla cross B, and then from the Ampere's law, and using for the law of the induction equation to the Faraday equation, it's written to like this. There. So this is important point. This is the time derivative for the magnetic field with the nabla times V cross B plus that this is the eta term is come to here. So this is double curl. It can be expanded from the vector identity. So this is also this equation is changing for this two equation. This second term, it's nabla dot B is including for here, but this is also becomes a 0 because of Gauss law. So nabla dot B equal to 0, so we can just drop off this one. Then left over to here. So this is we say this is MHD induction equation to using for the time derivative, time evolution of the magnetic field, including for the V cross B force times V cross B plus to that this is the eta, it's sigma is a resistivity term. Okay, so this is including for the induction equation. We can set up the MHD equation is also changing. So we are just only for the 1, 2, 3, 4 equation try to use them. Here the current is getting for to this magnetic field is the nabla magnet cross the magnetic field is getting for to here. Then electric field it's coming for the minus V cross B plus the J over sigma. So we just, if you get in for the magnetic field, it's time evolution. Then we can straightforward to get in for the density at the current and the electric field. This is the beauty for the MHD equation. Okay, so this is a more further simplification we can assume. We say most common use, this is an ideal MHD. So in case where the conductivity is very high, so this is the sigma is going to the infinity. The kinetic the electric field is just written to the E equal minus V cross B. So this is motional electric field only. Then it is known as the ideal magnetohydrodynamics. So the set of the equation is rather simpler. So we can just use it for this 4 equation. So this is the most simplest assumption for the MHD, but this is commonly used in the astrophysics situation because this is much easier to solve it for there. Okay, so magnetic field behavior in the MHD. So the MHD induction equation again to return to here. So this is we can now see about for these two terms. So first term is this is nabla cross V cross B. So this is we say domination of the convection term. So this is the infinity conduction limit. We can just use it for this left about this equation, this term. So this is the ideal MHD. So it means that the flow and the field are intimately connected, and the field line is compact with the flow. So we say this is a flux freezing situation. Then the flow is respond to the field is motion via J cross B force. So this is a very simple situation, and also very important point. The ideal MHD, the plasma flow and the field is connected. So every time it's a magnetic field, it's advected with the motion of the flow. And then a second term, this is Nabla square term is B, so it's been coming from the diffusion term. So this is the induction equation take the form of the diffuse equation, and then field line is diffused through the plasma and down any field gradient. Then so this is no coupling between the magnetic field and the fluid flow in this case. And then so characteristic diffusion time scale it's right here. So now it's just a Nabla equal to 1 to L. This is a spatial case. And the ratio of the convection the term and the diffusion term, we say this is magnetic Reynolds number. This is VB over L over the B over the lambda L square. So this is left over to here.
What is eta again?
Eta is this is the resistivity. This is opposite to conductivity. The one of the sigma equal to eta. Yep. So yes, here to sigma to eta. Yeah.
The ratio between those two terms is this number, magnetic Reynolds number. So that if the numerator is much larger than the denominator, resistivity is not important at all. The magnetic resistivity is
Okay. So yeah. Okay. So the next is also the rewriting for this continuity equation. And this is similarity to we can writing for the Nabla dot V to the V dot Nabla. So this is first term is getting for the compression to the fields contract or expand term. And then the second term is described for the advection of the motion of the fluid plasma. So similarity, we can try to use it for the induction equation. This is assuming for the ideal MHD case, can written as using for the standard vector identity. So this is the time derivative of the magnetic field. It's minus B Nabla dot V dot Nabla and the B dot Nabla term. So now we have a three component. So this is similar to compare to this continuity equation. The first term is coming for the compression of the magnetic field with the time. Second part is talk about for the advection of the magnetic field with the fluid velocity. Then third term is this is new term. It's coming for the stretching of the magnetic field. So it is related to magnetic field amplification. So based on to the fluid motion, we can also magnetic field is attracted with the magnetic field, then making for the amplification of the magnetic field with time changing for the time. So this is a completely new term for the induction equation, and this is also important for the dynamo effect. Okay. So this is the momentum equation. So from the equation motion and also continuity equation, we can coupling together. Then we are writing for the using for the definition of the magnetic stress tensor, the momentum equation is written to here. So this is originally coming from the both the equation motion and the continuity equation. You can little bit rewriting, you can get in for this equation. So it means this is also conservation form of the momentum to this equation. Then if you write in for this one, so m to the Nabla to the pi. So this is the Nabla at m equal to this is rho m over vi. This is the momentum density, and then this is pi I. This is stress tensor we say. So this is including for the ij. This is case there. Okay. So this is a conservation form of the equation. So this time I skipped to the making for the conservation equation, the energy conservation, but I think similar way to consider about for the mass conservation, the momentum conservation, you can get in for this energy the conservation equation also. So that now it's top panel, no, it's upper one is this is the mass conservation, the second one is the momentum conservation, and then third one is the energy conservation equation. And then we can coupling for the induction equation, and this is Nabla dot b equal to 0, derived b equal to 0, and then the equation state. So this is we say this conservation form of the ideal MHD equation. Why I can show you about for this conservation? because tomorrow I can talk about for the numerically solving for this equation. Then this conservation is a very important quantity to think about for the numerically solving. So here, I neglected the gravitational force, but of course we can include for this gravitational force inside external, or this is internally for the self-gravity term. And then this form is often used for this numerical simulation. Yes, I have already said. Okay, so the Poynting flux. This,
Just a comment.
Yep.
Um, actually, the system of equations
Mhm.
it does not include the divergence of v equal to 0 because
Yeah.
this
Okay.
is
Yes.
already,
Yes.
it was already implemented in the solution that allowed for the momentum, the induction, and the energy conservation equation. No, it's just a
Yeah.
comment.
Okay. Yeah. Yeah.
Yeah, no,
But-
I was wondering because it's 8 variables and 10 equations.
Yes.
No,
So,
divergence of
No,
v is
that-
already,
okay.
it's not an independent equation. It's not an extra equation because
But
it's
it
already.
should be used as a constraint, no?
It was
That's
used.
it. This is
This
yes.
is the point. It was already used as a constraint to get those equations,
But
right?
not for all equations.
All
Yeah,
the
yeah.
equations, it's already there. Just that I think Mizuno included this equation
Yep.
just to emphasize this point.
That
that
yes. Yes.
in the numerical simulations, you have to take care of this quantity, mainly in the boundaries,
Yep.
because it's not in order to make sure that you are not going to
Mhm.
create monopoles. Just this. But the equations itself, the system of equations, are only mass conservation, momentum, energy conservation, induction equation, and you
yeah.
close the system with the equation
So,
of
yes.
state.
Yep.
Everything else is evolved rho in the first equation,
Mhm.
v in the second equation, and internal energy E, small
Yep.
e, in the third equation, and B in the fourth equation. So you have.
But are you telling that if you solve the older equation,
Mhm.
Without this, yeah, it's okay.
the Gauss law should be obeyed automatically?
Automatic.
Yeah.
Yes.
Mhm.
It's not necessary to check if the conditions satisfy, because
Mhm.
this
I mean,
should be
you
a
When
see,
you-
what is your
When
opinion?
you use numerical,
I mean, we have a lecture. that
Yeah. Yeah. Of
has
course.
opinions.
No, of course. That yeah. This is analytically solution. We can. This is the fully involving for this. Yeah. Is Gauss. But numerically, we can. This is doesn't sometimes follow to this equation. So we need some new treatment to taking care. So
in
maybe
the boundaries.
yes, tomorrow I can talk about a little bit about how to taking care of this divergence free problem into the numerical one. So otherwise, if you solving for the analytically, this is fully construct. If assuming initially divergence b equals 0,
Yes.
yes, yeah,
it is clear, now you have talked about that this is an oversimplification
Yep.
to describe the
Mhm.
flaw
yes,
in the MHD regime.
yes.
But and then how you explain that this is often used in numerical simulation?
Yeah. I think it's most of the numerical simulations still using for this most simple situation, so either MHD.
So all simulations are wrong.
that's
No.
not
It's
true.
not. I say it's not wrong.
That's the answer to your
But this question has a deep implication, and it's very important to be discussed in this course because this is going to be a theory and numerical course as well. It's a small one, but this is a very important key point. And the question is that you can always include terms in those equations as long as you have a specific problem that requires this inclusion. So for instance, if we are dealing with resistive terms or dissipative terms, you have to incorporate new source terms on the right-hand side of this equation. And as a matter of fact, nowadays, there are several problems where you include these ingredients, and most of them will appear, like gravity, for instance, external gravity, will appear on the right-hand side of this equation.
And probably historically you start with the
The
simplest
simplest
situation.
form.
Yeah.
And
Mhm.
then you standard ideal MHD form, the simplest one. But most of the codes nowadays deal with these extra ingredients. Most of them as source terms on the right-hand side of those equations, right?
I think the most important part, of course, is resistivity or radiation. Or this is heat. This is everything coming for this source term. But yeah, situation it doesn't consider it here. Yeah. And also that yes, I think it's many cases just starting for the ideal MHD. Then case by case you can add to the new term. So add to the new component, new physics. Then how much changing to the situation. This is step by step we can doing for there to work now. So even for this MHD, so that everyone just starting for the hydro start initially. Then now it's think about the yes, still magnetic field important. Then we are concerned about the magnetic hydrodynamics. But still it's no, it's not enough. Then we can resistivity or heating or the radiation. So we can just go into the more complicated situation to the nature. Okay, for the Poynting flux. So from the energy conservation equation, so the energy flux is written to the here. So this is the half the rho b square and to gamma minus p is the velocity and the time to this magnetic field component here. So this component is hydrodynamic part and the magnetic hydrodynamic part, a magnetic part we say. So this is here is the hydrodynamic part and then this is the magnetic part. Now we can focus on to the magnetic part. It can be transformed here. So this is YEM. This is b square v minus v dot b dot b. So this is also calculate rewrite into this equation. This is v cross b is coming to here. Then this is v cross b. It's we say this is E, dense the electric field. So this is coming for the E cross b term. So this is we say we call the Poynting flux. This is the Poynting vector, which represents to the flow of the electromagnetic energy, how to moving from to the situation. So this is a very simple situation. So maybe you can see there. So the entropy conservation equation. Now I'm showing about this MHD equation. We doesn't include for to the entropy conservation equation here. But this is the entropy conservation equation. We can additionally add to this equation. So this is the best representative of this conservative form to the MHD equation. It's in terms of the variability of the density, variables, density, velocity, internal energy, and magnetic field. And the peculiar addition variable is the specific entropy S. For this adiabatic process of the ideal gas, this is conservation of the entropy. It's written to here. This is similar to the mass conservation. But this is not to the conserved form. So the specific entropy is moving with the fluid. The genuine conserved form is obtained by the variables times the density times this S. Then this is the entropy the per unit volume is written to here. We say this is the entropy conserved equation. And that, of course, this is sometimes we can coupling with this ideal MHD equation, how to change it for the entropy. And then in the numerically also we can try to use it for this entropy conservation equation, how to change it for this pressure or density, which independent to the case dimension.
So this is also a key point, because
Yeah.
he is a specialist in entropy.
Yeah.
It's DDST equal to 0 means entropy per volume conservation in each element of volume in the moving flow, right?
For a fluid in the
In the
sense
Yeah.
of the
yes, ds dt, the total derivative is the conservation in the moving flow in the element of volume, right? It doesn't mean that S has to be the same in every element of volume, right? But it's conserved in each element moving with the flow, right? So you imagine that you have the flow divided in several small cubes, parcels, right? So ds dt equal to 0 is conserved in the moving flow in each element, but each element carries its own S, right, entropy per volume, that is conserved in this volume element, right? But the neighbor elements may have different values for this entropy, right?
But for a perfect fluid, those equations are equivalent.
Uh,
For a perfect fluid, in the absence of
They are always equivalent.
in magnetic fields.
Mhm.
You mean these two equations, the Euler equation and the
The
Lagrange,
Lagrange
they are
equation,
always
yes.
equivalent.
Yep.
Just that the Eulerian describes in the frame, the fixed frame, right? So for instance, this.
Yes.
Yeah, I think this is a different observer situation.
The
That
conservation that
Yeah.
I present here for perfect fluid. Those equations are equivalent.
Yeah.
For a perfect.
Yep.
They have say,
Yes, 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 yes. Yep.
Mhm.
Okay, so this is the comparison with the hydro and the MHD equation. So the Newtonian MHD equation shows the coupling with the hydrodynamic equation with the magnetic field. So this is the equation for the this is again to the this is not conserved form. So if we can drop in for this magnetic the term, then we can recover for the hydrodynamic equation. So this is this is the mass conservation and this equation of motion and then the equation of state.
It's missing there the internal energy, the
Ah,
equation of
no, it's a but this is
energy
yes.
conservation equation.
This is conservative form, including for here, but this is the non-conservative form. We can just here, yes.
Still,
Yep.
we need an equation for the evolution of the temperature,
Ah,
right?
okay. Yes, yes.
It's missing anyways, but I think it's clear
Yep.
for everybody.
So this is the conserved form to the hydrodynamic case. Yeah, we just drop off the magnetic field. We can just see for the mass conservation, momentum conservation, energy conservation, and equation of state. This is familiar to equation. Yeah. So it's a little bit earlier, but it's a summary to the today's part. So the single fluid approach of the plasma is called the magnetohydrodynamics. Then in the case where the conductivity is very high, the electric field E is minus V cross P, it is known as the ideal MHD. In ideal MHD, magnetic field is frozen into the fluid. This is the most important the future or the behavior of the plasma into this ideal MHD case. The Lorentz force is divided into two diffusion different force. This is magnetic pressure and curvature. Sorry, I couldn't say this is part of there. Yes, yes, I missed it there. So the induction equation in the ideal MHD shows the evolution of the magnetic field. So it is including for the compression, advection, and the stretching term. And then to the induction equation, the resistive MHD, including for the diffusion of the magnetic field. Then from the energy conservation equation, so energy flux is composed of hydrodynamic part and the magnetic part, and then magnetic part is called the Poynting flux. So this is today's summary. I think everyone has already know about what the hydro and MHD. Then easy to recap about what here. So tomorrow I'm talking about what the how to solving for the hydrodynamic or MHD equation in the numerically. The most using for the finite different method.